Hi, my name is Håkan Silfvernagel, and today I'm going to be presenting why you should consider WebAssembly in your next front-end project. But before we start, I'm just going to give you some background information about me. So my background is I worked with human-machine interfaces for process automation and robotics, and I have also a master's degree in electrical engineering and a master's degree in behavioral science. I'm also interested in artificial intelligence and Internet of Things, so I've taken some classes in that. I am a Microsoft MVP in AI, and I'm also involved in the local community here in Oslo, Norway. So I'm part of Oslo AI and the Norwegian.net user group. So what is WebAssembly? Well, WebAssembly started out in 2015. All the major browser vendors got together and they formed a committee and they started to work on a standard internet standards draft that they published in February 2018. And what this means for us is that we can use WebAssembly in all the major browsers and also in the mobile versions of these browsers. So if we compare JavaScript and WebAssembly, we can see that JavaScript is a high-level language. It's flexible and expressive. It's dynamically typed. You don't need to compile, and you also have a huge ecosystem. Whereas with WebAssembly, it's a low-level assembly-like language. It has a compact binary format, and it promises near-native performance. So usually what you would like to do is you want to use a high-level language like C or C++ or Rust or Go, and then you can compile down these high-level languages down to WebAssembly. So we will take a look at how that is done in a short while. So as I said, WebAssembly, which is abbreviated WASM, is a new browser standard. It's based on a previous project called ASM.js. And it's an intermediate language in the same way as you compile Java down to bytecode or C# code down to MSIL. In WebAssembly, we have strongly types. So we have 32-bit integers, 64-bit integers, 32-bit floats, and 64-bit floats. So let's start to write a hello world program in WASM. Well, actually, we don't want to write a hello world program because we don't have strings or chars as types. So as you saw here previously, we only have float and integers. So the corresponding program for a hello world program is either an addition or a subtraction or a simple mathematical operation. So what we will write an add program here. So the WebAssembly has something called the WAT, which stands for WebAssembly Text Format. So we can define a module here, and inside that module we define our function called add2, and then we define what are the types for our input parameters. So we have two 32-bit integers, and what is the format for our resulting parameter. And WebAssembly is a stack-based language, so you can push and pop on the stack. So you get the first item onto the stack, and then the second item to the stack. And then after that, you can use an operation. So in WebAssembly, you have some 70 different types of operations that you can use. So in this example here, we are using an integer 32 operation called add. And then after that, we need to define what will this function actually be called. So the function will be exported as add2, and add2 refers to the function here in our module, which is also called add2. So there's a tool called what2wasm. So with this tool, you can have a look at what the actual binary file will be looking like. And as you can see here, it looks very much as an assembly type language. And there is also, you can also add a /v to this command, and then you can see what it looks like in a more textual format. So if we want to use WebAssembly, then the first thing that we need to do is we need to fetch our WebAssembly, and then after that we can read our WebAssembly into an array buffer. And then since WebAssembly is a web standard, we can just call WebAssembly.instantiate with this byte arrays that we just read in. And then we can use the results that we get from that. So we can call the result.instant and then exports and then the name of this function that we want to use, which is add2. So we can assign this to an object that we can also call add2, and then we can just use alert to have it output on the screen. So we do alert add2 and then input a couple of numbers. So this is the result that we get if we run this in the browser. So another tool that can be interesting to know about is something called the WASM Code Explorer. So what you can do with WASM Code Explorer is you can take a binary WASM file and then you can upload it to the WASM Code Explorer, and then you can see the textual representation of that file. So that's what we have done here. So we've uploaded this binary WebAssembly that we just made in the previous step, and then we can see that we get the same textual representation as before. But as I said, we don't really want to write WebAssembly directly. What we want to do is we want to use a high-level language where we can express ourselves much more freely, like C or C++, and in this case we're going to use Rust. So I'm going to give you a quick introduction to Rust. So Rust is a language that comes from Mozilla. It's a system program language with a syntax similar to C or C++. It's strongly typed, and you can compile it to native code. So one of the design goals with Rust is that you shouldn't have any memory exceptions. So you have a memory safe guarantee here when you're using Rust. So in Rust we have a tool chain with a couple of tools that we need to be aware of. So the first tool is called rustup, which is the installer for Rust. And second, we have something called cargo. So cargo is the Rust package manager. So in Rust, the packets that we're using is called crates. So when you create a package, then you can upload it to crates.io, which is the community package registry. So here's a simple hello world example here. We define a main function and we will print out a line, hello world, and then we can use Rust compile on our Rust file, and then what we will get is we will get an executable. So on a Windows system, we will get an exe file. So if we execute the main.exe file, then it will print out hello world onto the command prompt. Can also use cargo. So if we use cargo new hello world, it will create a new hello world project. So to generate the folder with a Rust file, with main Rust file, and also a toml file, cargo.toml. So what the toml file is, it's a package definition. So in this file, you need to define the name for your package and also the version and the author, and also if you have any dependencies on other crates. Then you can use cargo run, then it will compile all of this, and then it will run the resulting exe file, and then we will get hello world out on the command prompt. So in Rust, we have both primitive types and also primitive constructs. So the primitive types is Boolean, integer, char or string, and we have some primitive constructs like arrays, function pointers, and references. So what we want to do now is we want to use Rust, and then we want to compile Rust down to WebAssembly, and then we want to publish this WebAssembly up to npm. And then after that, we will create a very simple web application where we're using this WebAssembly that we have published. So how can we compile the Rust programs to WebAssembly? So the first thing is to install this Rust toolchain that we talked about. And then after that, we need to define a compile target. So we need to add the wasp32 unknown target in order to be able to compile to WebAssembly. Then after that, we need to install another crate called wasm-bindgen. So what this does, it defines sort of some glue code so that we can communicate from our calling application, which is in JavaScript, down to the WebAssembly. So as before, we have a package file, a toml file with the name of our package and the authors, and then we also need to define what kind of crate this is. So in this case, it's something called a C dynamic library. And then we also need to define dependencies. So in this case, we need to have this WASM bindgen in order to generate the glue file that we need. So we have a look at our main Rust file. So here we define that we're depending on an external crate, the WASM bindgen, and then we can also define here that we want to be able to use an external function, which is the regular alert function. And then we define our function that we want to be able to expose, which is called greet, which takes a string as an input parameter, and then it's just alerting it out. Then in order to pack this, we can use WASM pack init in order to package this into, first we will get the folder, which consists of 4 different files that we will have a look at. And then after that, we can just publish it as we do with any regular npm package. So we just do npm publish on the package, and then we can see our package, the Hello WASM Silver package, up on npm. But let's have a look at the content of this package. So we have a TypeScript file where it is defined what is this function that we can call from our application. So that's this greet function, and it takes a string as an input parameter. Then after that, we have this glue file, which is a JavaScript file. So as you can see here, it says export a function greet with an input parameter. And then it tries to pass a string down to our WebAssembly. And then it tries to also call the greet function, which is also defined in the WebAssembly. And then finally, it frees up the memory. And then we also have a package.json file. So in order for us to use this, we can create a standard webpack config file. We define an entry point, which is an index.js file. And we also have a package.json where we just have a dependency on our Hello WASM Silver npm package. Then we have an index.html file where we refer to our index.js file. And in our index.js file, we can import our npm package, the Hello WASM Silver package. Then we need to call this asynchronously, so we can call it js.greet, and then what we want to have printed out. And if we run this thing in the browser, we will have an output here, as we can see. So these were some introductory examples here, but now I'm going to give you a little bit more involved example here called Game of Life. So Game of Life is sort of a simulation where you have a game board, and then you have different types of cells that can either be live or dead. So there are some four rules that defines this simulation game. So the first rule is if you have any live cell with fewer than 2 live neighbors, this will die because of underpopulation. If you have a live cell with 2 or 3 live neighbors, it will live on to the next simulation. And if you have a live cell with more than 3 live neighbors, it will die because of overpopulation. And if you have any dead cell with exactly 3 live neighbors, it will become a live cell because of reproduction. So this will look something like this. So now we're starting our simulation here, and then we also have a pause button, so we can pause our simulation, and then we can. So now we pause our simulation, and then we can go manually and add some cells into the simulation and change the behavior of the simulation. So let's see how this has been implemented here. So as before, we have a cargo file with the name of the package, and the library, as before, it's a C dynamic library, and we also have a dependency on the WASM bindgen. Then we have our main Rust file where we define our game board with width and the height, and we also have some functions, some getters for the width and the height, and we also have a toggle cell function, which was the one that we used when we paused the game and we went in manually and activated some cells. And then we also have the TypeScript file where we're defining what type of functions can we call from a calling application. So we can call the width and the height in order to get back these numbers, and we can also call the toggle cell in order to toggle that particular cell. And also, as before, we have this glue file. So, for example, in the toggle cell function, it takes some input parameters, and then it tries to call the wasm.universe toggle cell. And then if we want to use this, we can create a bootstrap JavaScript file where we import an index file, and in the index JavaScript file, we define our game of life, our simulation board. And I've just marked here in red this universe.toggle cell that will be calling down to WebAssembly in order to activate that particular row and cell number. So now let's talk a little bit about performance, because as I said previously, one of the promises with WebAssembly is that you will have near native performance. So here they have done some experiments in 3 different browsers, in Chrome, in Firefox, and in Safari. And they've used JavaScript and JavaScript implementation and also WebAssembly implementation for the same algorithm. And what we can see immediately is that WebAssembly is faster than the JavaScript. But maybe what is more important is actually that you can see that is quite a high standard deviation in the trials for JavaScript. So you can see, especially in Firefox, there is quite a large spread in how long time this different computation takes. Whereas if you look at WebAssembly, it has a very small deviation. So that means that if you're using WebAssembly, you can be much more sure of the performance that you will get, because it doesn't deviate as much as from JavaScript. We should also take into account that JavaScript has been around for quite a long time, so the JavaScript engine has been able to be optimized, whereas the WebAssembly has been around for much shorter time, so we can expect better performance with time. So now I want to go through a couple of examples here from the real world. So one of the examples is a digital signal processing library. So here there are some people that had a digital signal processing library written in C, and then they wanted to expose this library so that they could use it on the web. So they exposed it through WebAssembly. So it looks like this. So here you can see that you can use this different kind of transformations in real time here, both on static images but also on live videos. So this is a good use case for WebAssembly, that if you already have some code or some libraries in C or C++ or some other language, and you want to expose this library on the net, that's a good use case for using WebAssembly. Another example is from AutoCAD. So AutoCAD has a lot of drawings for buildings and constructions. So what they wanted to do is they wanted to be able to expose this on the web. So they built an AutoCAD web app where they are using a WebAssembly. So we're going to have a quick look at how the architecture of this web app. So on the front end, they can use any type of JavaScript framework like React or Vue or anything, and then they already have their domain-specific libraries in C++ code. So what they did was that they exposed this C++ code through WebAssembly, and so that you then could call this from the React front-end code. So I think this is a good example also of separation of concern. So this means that you can have your front-end developers can focus on the front-end development, whereas you can still have your domain experts working on these C++ libraries that they have done in the previous years. So what are the future plans for WebAssembly? So one of the things that they would like to be able to do is would like to be able to call WebAssembly directly to change the DOM or to call a web API. So as you saw now, we need to import this crate in order to get the glue file that we've seen in all of these examples. But they want to be able to get rid of that. Then another thing is that would like to be able to directly import WebAssembly into JavaScript, just like a regular import. Whereas now you need to load the WebAssembly by making an asynchronous call. And they would also like to be able to support more languages. Like any right now, it doesn't support managed languages like Java or C#, but that's something that they have in plans for the future. I would also like to talk a little bit about serverless WebAssembly. So WebAssembly is not only for the browser. You have some providers like Cloudflare and Fastly that supports WebAssembly on the server side. So what this can give you, it can give you fast launch times, and also you don't need to rewrite your server-side code to JavaScript. So this is an example here where we can see we have different types of, if we have a generic data processing application with a front end and a back end, then either we can have a front end and then we do the data processing in the back end, or we can do the data processing in JavaScript, all client side, or we can do it through client side WebAssembly. So we can convert our algorithms, maybe written in C, into WebAssembly, or we can have it run as a serverless WebAssembly. So then you also have your data processing algorithms in C, and you can compile it to WebAssembly and call it from there. Then we will have a quick look here at some other frameworks which are also using WebAssembly. So one of them is AssemblyScript. So AssemblyScript compiles a subset of TypeScript to WebAssembly using a different compiler called binary. So one thing that we need to take into account is that we don't have any garbage collector. So if we're going to use AssemblyScript, we need to allocate and deallocate memory ourselves. So this is a small project. We have some sponsors, but it's nothing like, with Rust that has Mozilla backing them up. Another example is with Blazor, which is a Microsoft framework. So with Blazor, you can either have Blazor running on the server, so then you have client events that will be sent back from the server using Signal R up to the client, or you can have it run on WebAssembly. So then you have a particular port of the .NET framework, which runs on WebAssembly that you can use. So one important question is this the new old thing? Haven't we seen all of this before? So in the past, we've also had some frameworks that has given similar promises like ActiveX. We've had Flash and also Silverlight. But I think one important difference from these frameworks and WebAssembly is that now WebAssembly is actually a standard that is supported by all major browsers, whereas these were all proprietary formats. So I think that is a good promise for WebAssembly. So what is the conclusion here? Should we do WebAssembly all the things? When I first started to look at WebAssembly, there was a lot of articles saying that JavaScript is dead and WebAssembly will take over everything. But I don't think that is actually the case here. I think WebAssembly is one tool which is good to have in your tool belt. And it's especially good in some use cases, like if you already have a C or C++ library that you want to be able to expose on the net, is a perfect use case for WebAssembly. But as of now, it's quite complicated to do some more sophisticated things. So you just have to weigh the benefits from the drawbacks. So I also have some references if you want to learn more about this, and if you you want to reach me, you can reach me either on Twitter, or you can also reach me on my email. So with that, I would like to thank you all for your time. Thank you so much.